Okay, so let's talk about linear combinations, right? So let's say we're given some W. All right. So say what is dW if d is going to be greater than or equal to 0? Well, dW if d is greater than or equal to 0, this is going to keep going on forever. Okay, what if we decided we wanted the spanning set to be even bigger? So let's say, yeah, we'll do W. That's infinity. Not just infinity, but you get the idea. Okay. So if we let W span both positive and negative as far as you want to go, well, what we get the entire one. Okay. So in general, when we talk about spanning sets, we will let D just be any real number. And our spanning set, so if we said any scalar multiple of a vector W, it'd be the entire line that is parallel to that vector W, okay? It's just stretched out as far as you want to go. Right? Let's say if we wanted to do some restrictions onto this. So, all right, let's say use the same W. And then let's add in a V. Right? So let's say we're going to look for CV plus DW where C is going to be greater than or equal to 0. And 0 is going to be less than or equal to D, which is going to be less than or equal to 1. So C can grow as much as you want. C can also shrink V, okay? And so C is just going to grow greater than or equal to 0. Okay, fine. So it could be, maybe 1/2. It's just going to go all the way up this way. Like that. Okay. Now W is going to, the only thing W can do is it can either remain the same with D equals 1 or it can shrink. Okay? So, that. So we can have a vector smaller than that. And now you have to imagine this, the sum of these two vectors. If I start drawing parallelograms, if I drew a parallelogram between this vector and this vector right here, we're going to end up like right there. Okay? Now if I did this vector and this vector, we're going to end up somewhere like right there. Okay? Or I could do this vector and let's say that vector, and if I drew a parallelogram, I would end up right there. So what is the sum of CV plus DW? So since W can shrink and V can grow, we're going to draw all possible combinations . Okay. So this would be so all vectors with terminal points that lie within that shaded region, and that shaded region keeps going off towards infinity because C is not bounded from above. It's bounded from below by 0. But okay. So let's say we did these two same vectors. W and this is V. All right. And we said CV plus BW, where negative infinity is going to be less than C, which is less than infinity, and 0 is going to be less than or equal to D, which is going to be less than or equal to 1. Okay? Well, W is still stuck in that region right there. V can grow as much as it wants in that direction, and also as much as it wants in that direction. Okay, so we end up with this infinitely long rectangular region in R2. Okay? Well, what if we didn't put any restrictions on C and D? We just said C and D can be any real numbers. So So now in this case where we don't put any restrictions on V and W, what is this going to do? Well, all right, that's not the greatest picture. That's all of R2. So as long as the vectors aren't parallel to each other, if you have two vectors and you talk about their spanning sets, well, if they're, and what do I mean by being a basis? They're going to form all of R2. So V and W can serve as a basis for R2. So in two-dimensional reality, you only need two vectors to actually form a basis of that, well, two-dimensional reality, okay? Unless they are parallel, okay? And so if they're parallel, that's what we would refer to as linearly dependent, okay? Now, let's talk about this idea of dependence versus independence. And we'll get into some exact definitions of what I mean by dependent versus independent. But this makes more sense in higher dimensions, okay? Okay. Now, let's talk about the standard basis for R3. Okay. We got E1, which is 1, 0, 0. E2, 0, 1, 0. And E3, 0, 0, and 1. Okay, so now C E1 plus D E2, not going to use it me, that's a F E3, where C, comma D, comma F are just in the reals, okay? This forms all three-dimensional space. Okay? Where, what if I said, you know, C E1 plus D E2, for C comma D are in the reals. That just forms the XY plane. All right. Let's say I did DE2 plus F E3, where D comma F are in the reals. Okay. So what is that going to do? That's going to form the YZ plane. Yep. All right. So let's say we had two arbitrary vectors out in space, okay? And so instead of the standard basis, okay? Okay. So let's say that this guy is in the YZ plane. Let's say this guy is in the XZ plane. Okay. Now these two vectors, call that W. All right. So okay. So if you have two vectors in R3 that are not parallel to each other, then they're going to form a plane, and it's going to be a plane that passes through the origin as long as we have our standard vectors that begin at the origin. So I mentioned something about linear dependence a minute ago. Now, the concept of linear dependence when talking about these types of spanning sets, we're going to talk about linear dependence in a lot of different ways. But what is meant in the three-dimensional sense by linear dependence, okay? Well, if you have three vectors in R3 that are linearly independent of each other, I was also talking about basis. I'm going to mention things that we'll do some precise definitions later on. So what does it mean for three vectors in R3 to be linearly dependent? Okay. Well, what that means is that all three of those vectors, they lie in the same plane. And since they lie in the same plane, you only need two vectors to form that plane. Okay? Well, that means that since you have a third vector that's already in that plane, well, those other two vectors could make up that vector, and vice versa. And when you say that something that vectors are linearly dependent, in the sense in R3, all three vectors will lie in the same plane, okay? It's not that one vector is a bad vector that is the one that's making them linearly dependent. All three of them are dependent because they all lie within that one plane, okay? So that's what's meant by the sense of linearly dependence. So what does linearly independent mean? Well, that means that you got two vectors in that plane, and then you got a vector that's sticking out of that plane. So if you have two vectors within a plane, okay, so I'm just gonna go ahead and draw this as a plane. Say V, and say W. And let's say U. Okay? So CV plus DW plus, let's say, FU, where C, comma, D, comma, F are in the reals. Okay. So three vectors in R3, they'll form all of R3 if you allow their spanning sets. Okay. So now, okay. Okay. So this is the difference between dependent and independent when it comes to R3. So there's actually a precise definition that we will be using later on of exactly what it means for something to be dependent versus independent. But when thinking about this, this is the way you want to think about it. And so you can see that within this linearly dependent set, they're all three in the same plane. So it's not like one of them is bad. Any combination of two of those vectors would actually end up forming that plane, okay? So, yeah, that's the difference between dependent and independent. So if you have a spanning set that's just within a plane, then it's not going to form all of R3.